All right. Welcome back, everyone, for some quantum algorithms now. So the first talk of the session is going to be given by Teal Witter from Middlebury College, and he's going to tell us about applications of the quantum ST connectivity algorithm.
Awesome. Cool. Hello. Does the microphone work? Cool. Okay. So today I'll be talking about applications of the quantum ST connectivity algorithm. My co-authors are Kai DiLorenzo and Shelby Kimmel, and my name is Teal. So I'll start by going over some of the layers of abstraction of today's talk. So at the very bottom, we have quantum gates and quantum circuits, so what we're actually running on the quantum computer. Above that are span programs, which all you need to know about these are that they're linear algebraic objects that we can use to solve interesting problems, from graph theory to Boolean formula evaluation, truly a wide variety of problems. One of the span programs is particularly interesting is that of ST connectivity, which tells us, given a graph, whether two vertices are connected, whether there's a path between vertices S and T. This talk and our work today will be about reducing other problems to ST connectivity and exploiting some of the nice complexities of the ST connectivity span program to solve these problems efficiently. So at the very bottom, quantum gates. Above that, span programs that run efficiently on them. ST connectivity is a span program, and that's what we'll be using. The first part of today's talk will be explaining the ST connectivity span program and the complexity of it, and then I'll be talking about how we reduce other problems to ST connectivity. So the recipe that we use for our results is to first encode a question into a graph structure that we can answer by determining whether two particular vertices are connected. Then we need to analyze the worst case effective resistance and capacitance of this graph reduction that we create to tell whether we can efficiently determine whether two vertices are connected on this graph. Sometimes also in the process of encoding these problems into the graph reductions, we're able to encode characteristics of the original graph that are interesting. So if we look at the reduction and we solve for and estimate quantities in the reduction, we're able to determine quantities of interest to the original graph that we consider. So the big question that I have for you today is, given that ST connectivity reduces quantum algorithm design to a simple classical algorithm, you don't need to know anything about quantum gates or quantum circuits or phase estimation to be able to use ST connectivity. You just need to know about ST connectivity, which is very much a graph theory problem. Given that ST connectivity reduces away a lot of the quantum of this problem, and even though ST connectivity feels natural in the following ways, it's optimal for a wide range of problems, including Boolean formula evaluation and total connectivity, and it's easy to analyze using effective resistance and capacitance. So it's not quantum, but it has the nuance that you would expect from something that isn't at this layer of abstraction. ST connectivity is high above quantum gates and quantum circuits, but we still have some nuance to the problem, and we're able to exploit this to find optimal solutions and algorithms for the problems that we'll consider. So does the ST connectivity approach that we consider today give intuition for the optimal underlying quantum algorithms, even though the approach to these problems will be very classical? So I'll first begin by going the ST connectivity algorithm and how it works. So we're given a graph, a set of vertices and edges. The circles denote the vertices, the lines denote the edges, and we want to know whether two particular vertices are connected, whether there's a path between them. Here, the dotted line indicates that an edge is not present, so there's no edge between S and T, but there is an edge between S and U, and there's another edge between U and T, so we can say that S and T are connected on this graph. But if we were to consider a graph that looks like this, where we take away the rightmost edge, then there would be no path from S to T. One of the ways to see this is that the component connected to S is made up of S and U, whereas the component connected to T is made up of T and V, and there's no edge between either of these components, so we're able to cut, which means that we're checking all of the vertices between these two components, and we can tell because there is no there are no edges between these two components, there's no path from S to T. The query model that we consider for this problem is that we're given as input two things. First, the graph skeleton, which means that we know where all of the vertices are on this graph, and we know where all of the edges might be. And then we're given a hidden bit string, which tells us whether each edge is actually present. So for example, in this problem, we're given a 3-bit string, and the first bit corresponds to whether an edge is present between vertices t and u. So for example, if we're given the bit string 1, 1, 1, we know that the graph looks like this, and there is in fact a path from S to T, so we should output that the S and T are connected in this graph instance. But if we're given the bit string 0, 1, 1, for the same reasons that we're able to find a cut between these two components, there is no path from S to T. Our goal here is to minimize the queries to the bits. So we're given a hidden bit string, and of course we need to uncover some of the bits to tell what the graph looks like, but we want to uncover as few of them as possible, as few of these bits as possible, to determine whether S and T are connected in this instance of the graph. So in terms of part of what makes this algorithm so nice to work with is that its complexity is very nice. So what do I mean by that? Its space complexity is logarithmic to the number of edges in the skeleton graph, and we inherit this property because it's a span program. The second thing that makes it particularly nice, and is the nuance that I was talking about earlier, is the query complexity, and that's the square root of the maximum over all the connected graphs of the resistance from S to T times the capacitance over all the graphs where S and T are not connected, and the maximum over these. And I'll talk about these two quantities later, but effective resistance is really a measure of how well connected S and T are on a particular graph, so it makes sense that the bound for the ST connectivity problem is how hard it is to get from S to T when S and T are connected, times the amount of work that we need to do, which is the cut or capacitance when S and T are not connected. And the time complexity is a little more complicated than this, so a lot of the time we want to work with query complexity, especially because we can easily compare it to classical bounds. But in this case, the time complexity is the query times the time it takes for a quantum walk on the skeleton graph, but we're not actually implementing a quantum walk. We're doing phase estimation on a unitary built from the quantum walk unitary. So to explain these two concepts, we'll first start with the resistance on a particular graph. So if S and T are connected, you can think of a unit flow starting in S and going to T. And the flow optimizes itself along all of the edges in the graph. So in this particular case, there are two paths from S to T, each of length 2. So we're going from S to T along one and along the other, and the flow distributes itself symmetrically because these two paths are symmetric to find the ideal flow from S to T. What you need to know for the rest of this talk is that the resistance is bounded by the longest path. So the worst case resistance that we could get is a very long path from S to T. But if we're able, even if that path is very long, if we're able to find a lot of long paths from S to T, then we can decrease the resistance. The capacitance is the analog to the resistance in the case where S and T are not connected. You can think of this as a charge of 1 at S and a charge of 0 at T. And what you need to know for the rest of the talk is that the capacitance is bounded by the biggest cut on the graph. So in the worst case, part of the analysis we'll be doing is that you'll just have to check all of the vertices, or all of the edges on the graph, in the very worst case, to determine whether S and T are not connected. And for the problems that we're considering, that'll be okay. So that's a little bit about ST connectivity and the way it works and its complexity. The next half of this talk will be about the problems that we actually use that we reduce to ST connectivity. The first of these problems is cycle detection. So we're given a graph and we want to determine whether there's a cycle on this graph. A particular edge is on a cycle if you can leave that edge and return back to it without going on the same edge twice. So we want to encode this problem in terms of a particular, leave that vertex, and come back to it without going on the same edge twice. We want to encode this instead of being about a vertex to being about an edge. So we want to ask the question, is edge I between, let's say, vertices U and V on a cycle? Well, it's on a cycle if and only if that edge both exists. It actually has to be in this instance of the graph, and there's a path from U to V that doesn't include edge I. You can see that if both of these conditions are met, then that edge is on a cycle, and both of the vertices that it's connected to are also on a cycle. So we would start at V, go to U on edge I, and return back to V from U without going on edge I. And that's the conditions for a cycle to be present. So we want to encode this as per our recipe in a reduction, a graph that we'll call a reduction. In this case, that's the graph on the right-hand side, and we're going to use ST connectivity to answer this question. So we want to know whether S is connected to T. Because the two conditions are an AND, we need both of them to be true for edge I to be on a cycle. We're going to set things up in series, so we need to get first from S to U in this particular case. We need that edge to be present, and we also need a path from U to V in the original graph. So when we have two things that are ANDed together in this case, we want to set them up in series, so the only way we can get from S to T is if both of them are true. Here, the first part of this is very self-explanatory. We just say that the edge I is now between S and U, but the second part of this is a copy of the initial graph with edge I removed. And you can see if both of these conditions are true, then edge I exists, and there's a path from U to V that doesn't include edge I. So that answers the question for a particular edge. We want to ask this question about the whole graph. And for there to be a cycle on a graph, we need some particular edge to be on a cycle. So we're going to set all of it, whereas before we set things up in series to denote an AND, now we're going to set them up in parallel to denote an OR. So we're able to get from S to T if any of these edges is on a cycle. And that's what this graph does. We have many copies of the initial graph with each one of the edges removed and moved up, so it's now connected to S. And I was lazy with the graphics here, so that's what this is. The dotted lines denote copies of the original graph. So when we come to analyze the complexity, hopefully I've convinced you that this graph, if there's a path between S and T, then there's a cycle in the initial graph. But this graph is significantly larger than than the initial graph that we had. There are the number of edges, let's call that M, copies of the initial graph, so it's very large, and you wouldn't think that we could run ST connectivity efficiently on this graph. But we actually can, and the reason for that is that the resistance is constant. The way to see this is very interesting. So consider a graph with a cycle of an arbitrary number of edges. Let's say there are 10 edges on a cycle in this initial graph. It's true that the path from S to T in our reduction will be of length 10. We have to go on 10 different edges to get from S to T. But we'll have 10 different copies of that path because we have a graph for each one of the edges that's on a cycle in the initial graph in our reduction. So we can have a very long path, but we have lots of these long paths because for each edge on that long path, we have another one of these graphs that are set up in parallel, so we're able to distribute the flow very efficiently from S to T. So we pick up a constant resistance, which is very interesting, and we'll talk a little bit about this later. Now we have to consider the capacitance of this graph. The first thing to note is that the capacitance is on a graph when S and T are not connected, which means in our original graph that there is no cycle, which means that the number of edges has to be big O to the number of vertices in the graph, because if we have more edges than vertices, then we'll necessarily have to create some cycle. So we know that the number of edges that are present on our graph where there is no cycle is less than or equal to N in big O. For the rest of the graph, for the rest of the edges in the skeleton, we can just do a simple cut and check whether the first edge is not present. A lot of these edges aren't present, so we don't need to worry about them. What we do need to worry about are the edges that are present in the graphs where S and T are not connected, so there is no cycle. There are N of these graphs, and for each one of them, in the worst case, we can just check all of M of the edges in the skeleton. So the capacitance and the cut that we pick up is N times M, which gives us a total complexity from before of the resistance, square root of resistance, which is still constant, times the square root of the capacitance, which in the worst case, M is N squared because there are N choose 2 edges in the graph because it's a subset of the complete graph, and we can pick up N to the 3/2. We can compare this to the existing bounds. The lower bound for this problem quantumly is N to the 3/2. The previous bound is logarithmic N to the 3/2, so we can improve on this slightly to match the lower bound using this approach. So that's the first problem that we consider, but what should strike you about it is that the resistance of this reduction that we create, even though the graph is very large, is constant. And there's a little more to say here. So it turns out that the resistance of the reduction that we create is inversely related to this quantity called the circuit rank of the initial graph that we consider. The circuit rank has a lot of applications in a variety of branches of mathematics, but it's the number of edges that we need to cut until there are no more cycles on a particular graph. And I won't explain precisely, the relationship between these is precise, but I'll give you an intuitive understanding for why these two quantities are inversely related. So if the circuit rank is higher on the initial graph, that means there are more edges that we need to cut until there are no more cycles, which means on the reduction, it's easier to find a graph and an edge that's connected that gives us a path from S to T, which means that the resistance is lower. So that's an intuitive understanding for why these two are inversely related, and of course in the paper we go through a proof about why they are precisely inversely related. So we can use an algorithm due to Ito and Jeffrey from a 2015 paper to estimate the effective resistance of the reduction, which tells us about the circuit rank of the initial graph, and we can do it in this time where epsilon is the multiplicative error, and we can improve on this in the case of a cactus graph. We are familiar with no lower previous bounds, so we think it's really exciting that we can estimate the circuit rank of the graph in this way. The next problem I'll be talking about is even length cycle detection. We can also do odd length cycle detection, which is bipartite detection on a graph, but lots of other papers deal with that, so we'll talk about even length cycle in the talk today. If there is no even length cycle on a graph, then we know that all the cycles must be odd. If we have two odd cycles that share even at most one edge, then there's a way we can walk around both of these odd cycles and we can make an even cycle. So this algorithm actually tells us if there are no even cycles, that there are also no connected cycles on this graph. We're going to ask the question in a similar way we did before: is edge I on an even cycle? As before, it has to exist, and this time there has to be an odd length path from U to V that doesn't include edge I in the initial graph. So we want to encode this in a reduction. Our reduction looks like this, which is the bipartite double of the original graph, which just means that we're copying all of the vertices, and then we draw an edge between the left and the right side if that edge is present in the initial one. So here, there's an edge from U to X in the initial graph, which means that we connect the left U to the right X and the right U to the left X. So that's where this graph comes from. And you can see that if there's an odd length path from U to V, which I'll now denote with a capital T as I did before, then there's a way that we can get in an odd number of steps from U to V, because if we're like crossing over from one side to the other, then it must necessarily be odd. If we go back and forth, then we'll still be odd. So we need there to be an odd length path from U to V, and we also need edge I to exist. Because this is an AND condition, we set things up in series as we did before, and this answers the question again only for a particular edge, and we want to ask it for all edges in the graph. So we'll set all of these questions, or these like graphs, copies of the bipartite double copies of the initial graph, up in parallel. So if any of them are true, then we can get an OR on any of these. As before, for similar reasons, the complexity is n to the 3/2, and the resistance is constant. We suspect that there's also another characteristics of the initial graph, similar to circuit rank, hidden in here, but we haven't found it, and this is an opportunity for future analysis. So this is our solution to the even length cycle detection problem. In terms of previous bounds, we're familiar with no quantum lower or previous bound. There is a classical bound, which is tight n to the n squared, and our bound improves on that again, n to the 3/2. Great, so now I'll talk a little bit about open problems. The first that I kind of hinted at before is that we've only shown query complexity in part because it's very simple to analyze for these graphs, but because the graphs that we're creating are so large, it's harder to show that the time complexity is asymptotic as we suspect the query complexity. So one area that someone could do going forward is a full analysis of the highly structured reductions to show that they are time efficient, and we suspect because of their significant structure that this is possible, and we suspect that it is time efficient. Another area of research is to extend the cycle length detection to an arbitrary modulus. Here we're able to show whether the graph is, or to determine whether it's an odd or even length cycle, but maybe you could determine that like mod 3 or mod 5 or something like that. All the problems that we considered are in the symmetric logarithmic complexity class. So, and we've been able to meet what we think are the optimal bounds for all of these algorithms. So we're curious whether if we can reduce other symmetric logarithmic problems to ST connectivity and whether that always gives an optimal algorithm. And finally, to get back to the problem that or the question that I gave to you at the beginning, does the ST connectivity approach give intuition for the optimal underlying quantum algorithm? This is very vague, but hopefully, even though there are no quantum circuits in this talk, you've gotten a sense that what we're dealing with is incredibly nuanced and precise, and hopefully can give insight to the optimal underlying quantum algorithms that we're attempting to find. So thank you for listening, and also thank you to my co-authors, Kai and Shelby.
Thanks. We have time for questions. I have a question, which is that just in general, classical algorithms, so people have identified problems that are complete for certain times, like linear time, quadratic time, such as the three-sum problem, for example, or other such problems. So did you look into that? Is there any chance such a similar thing could be done in the quantum case? So these are for time complexity, but I guess you could also ask about query complexity.
Sorry, I didn't really understand the question.
The question was that for classical algorithms, so there are some problems that are known to be complete for linear time algorithms or quadratic time algorithms or cubic time algorithms. Like an example is the three-sum problem that's complete for quadratic time. So I was asking, because here you chose the ST connectivity problem as sort of a base problem, and so I was asking why is that, and if there would be a more general theory of reductions in the quantum case.
I don't know if I have that much insight into this, but just from working on this problem, it seems like the symmetric logarithmic complexity class gives us the broader complexity that we're talking about. I don't know. Does anyone have insight?
Okay. Yeah.
So you described the decision problem are SNT connected. Do you have any? Can you elaborate on the Sharpie version of this? How many paths between SNT or?
Oh, explain that. Why there are so many paths?
What is the complexity of counting the number of paths?
Of counting the number of paths between S and T? As a different problem, if that's what we wanted to do. I am not familiar with anything along those lines, but I know that we can estimate the effective resistance of a particular graph that we create, and of course the number of paths have to do with the effective resistance. So maybe if we knew the length of each path, then that would tell us, if we knew the number, that would tell us the effective resistance. So if we could estimate the effective resistance, then we could figure out the number of paths if we were given a specific length of the path, but I'm familiar with no other algorithm off the top of my head to do that. Thank you.
There was one more question. Yeah, let's take one more question while the next speaker sets.
So if I understand correctly, so one of the advantages of doing this way, other than designing algorithms with this ST connectivity framework, other than the fact that you don't have to talk about quantum, you can just do it by reduction, is that the ST connectivity algorithm uses only log space, and this was nice. So does it also follow that all the algorithms that you presented today also only use logarithmic quantum space?
Yes, that's true. Which is part of I didn't talk about this, but that's part of the reason that we're able to make them so large, is because it's still logarithmic to the number of edges. And multiplying by a factor of the number of edges only adds that in logarithmic space. So we're able to inherit that property, which is another reason it's really nice to work with this problem.
Thanks.
So the reductions are log space reductions, just to make sure I got it. Okay. Okay, let's thank the speaker again.